suppose you have a vector space, and let's say this list A, V1, V2, Vn is a basis for V, and this is an inner product. So you're given an inner product, you're given a set of bases. Now the goal is to come up with a new set of bases so that two things happen. Every element in this basis are orthogonal to each other, and every element in this basis has size 1. Okay? That's what you want. Right? So what you do is, so then define, okay, step 1, let U1 be, take V1 and divide it by its size. See, if you have an inner product, that automatically defines the norm, right? So we have the norm as well. And what you do is you take the very first element and divide it by its size. What does this do? Makes it a unit vector, right? It resizes it so that the size is 1. Okay. Now, step 2. What are you going to do to make this second one to be orthogonal to U1? Well, what you do is you take V2, subtract V2 and U1 inner product times U. And then we're going to call this U2, but the problem is this is not going to be a unit vector, so you divide it by the same thing again.
And that's to get that it's orthogonal?
The first part is to make it orthogonal, U1. And then the second part, dividing by it, would give you unit vector. Now, check. Let's see what we get if I do U1 inner product with U2. Okay. So U1 inner product would be V1 over, well, you know, I don't need to actually rewrite U1. I'll just leave U1 as U1. I'll replace U2 as V2 minus V2 U1 over norm of something. Now I want to show that this is 0, so a constant doesn't mean anything, so I'll just bring it outside. Using linearity, that comes outside, right? Now I can use the linearity of the inner product. So I can do U1 V2 and U1 of this. So let's just call this K. I'll just call this K. Okay? So it's going to give you U1 V2 minus U1 times V2 U1. Okay? Now let's see. This is just a number. It looks horrible. That's still a number. So what can you do? We can bring it outside, right? So we can bring that outside. And make it V2 U1, and then it will be just between these two. Okay, here's a question. What is U1 U1? any vector inner product with itself is same as?
It's a positive definite property, right? So
Yeah,
it's
but then
squared.
it's norm squared, right? What's the norm squared of U1? What's the size of U1?
Itself.
No, what's the size of U1? We did some. 1, right? It's a unit vector, right? It's 1. So it's 1 squared. This is going to be 1 squared, which is just 1, right? But so now it's just this minus this, but then we're working with a symmetric product, right? Symmetric inner product. So you can switch, and what do you get?
0.
0. So what does that show? We just proved that these two vectors are orthogonal because their inner product is 0. If dot product is 0, then the angle between them is 90 degrees. Okay. So that's how this works. Okay. So now, eventually, if you're convinced of this, then you can eventually see how to do the next one. Okay? So let's just do one more, and then I'll write down the general formula. Step 3. We're going to define U3 as what? V3. And what I'm doing is I'm going to take out the component of V3 that's in the U2 direction and subtract times U2. And take the component of V3 that's in the U1 direction and take it out. And it's really helpful to know if you know that if U is a unit vector, then the component of any vector V in the U direction is just simply V dot U. Okay. So if you know this, then you kind of know what this is doing. You're picking up, so here's what it is. You have V3 and you have a unit vector U2. And what this does is, this inner product measures this much, this length. And you're subtracting this off. Since you're subtracting, what does it do? This much is taken away, and now V3 minus this much gives you this new vector, and look what happened. This is now perpendicular to this other one. So you're making things orthogonal by taking out the component in that direction. That's what this is doing. And then you divide by the size of the entire thing, so that again you have a unit vector. Right? So you have a unit vector, and you just keep doing this until you get to step n, right? So what will be the step n? You will define un for the last one, right? And it will be vn minus vn, and then un minus 1, un minus 1, and then minus da 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 da, minus vn u1, u1. No, it's just like da da da, everything I'm skipping, right? And then this divided by the same thing. Okay. So if you do this, then at the end of the day, another point of concern is, what if the denominator is 0? Always when you divide, you have to worry about that, right? But then if any of these become 0, then you're saying that this is equal to 0, which is saying that Vn is the linear combination of previous ones. And these are already linear combination of the previous vectors. So if any of the denominators become 0, you immediately have a proof that this is not a linearly independent basis. It's not a linearly independent list. So that can't happen. Being a basis precludes the denominator from being 0, so you can carry this until step n. And if you do this, then the outcome is, then u1, u2, until un is an orthonormal basis, ONB. Okay? ONB means orthonormal basis. And the nice thing about this is if we call this basis as B, then your original inner product that was used to build this basis under this basis B would look like the identity matrix. Okay. 0 everywhere else, it's just this. So that under this basis, the inner product looks like the usual dot product. And it simplifies so many things. Okay? So that's the point of Gram-Schmidt. It's used in so many different contexts, even in numerical analysis. When you try to solve some large system of equations, you end up using this in some cases. So it's a very powerful method. It's simple in idea, but it has many consequences.